Hey everyone, welcome back to week 4 of Azure Cert Prep. And today we'll be delving more into relational databases. We talked about the different kinds of databases, relational, non-relational, OLTP, OLAP last week. This week, we're going to talk a lot more about relational OLTP databases. We're really going to go through every single category of database within this course. So yeah, today, everyone, we're just going to solely focus on relational databases and auxiliary objects like views and procedures. We'll also delve into a little bit of SQL. And finally, we'll talk about the concept of normalization. We actually talked about almost all of these concepts we actually talked about throughout the fellowship. So really think of this as a rehash of the concepts that you've seen in the past year, as opposed to something that's completely brand new. You should recognize at least some of these keywords. And as always, please make sure to watch this video at 1.25 or 1.5 speed. Yeah, and pause and take breaks. Definitely don't consume this all in one sitting. Anyways, let's dive right into it. Yeah, SQL jokes are always all the rage. Here's a license plate designed to drop the ticket database of like a traffic authority or something like that. I believe this person was from Poland. And basically what they did is on top of their license plate, they put this SQL query so that when a camera snaps their photo for speeding or running a red light, it reads that license plate, including that term drop database. It gets fed into the system, and theoretically, it will drop everyone's ticket information. So therefore, the traffic authority will not be able to ticket anyone because the database is gone until they recover it, right? Anyways, SQL humor, always a good thing to fall back on. Let's keep moving forward. All right, so here are a couple of review questions that hopefully you should all be able to answer after reviewing last week's notes and readings. Once again, take a minute to think about this answer, and then, yeah, we'll answer it during the video, and let's see if you got it right. Okay, question 1. What is a transaction? Go ahead and pause the video, think about it. Your answer should be a single unit of work. That is all that a transaction is. It could be multiple operations in one transaction, but that doesn't change the fact that it is one single unit. Next up, which ACID property guarantees that either all operations of a transaction succeed or fail? Pause the video, think about it. Okay, and that is the atomic property, right? Either everything works or nothing works. There is no such thing as half complete transaction. Think about the solar flare example. If only one part of the transaction completes, but the second one fails, the entire transaction needs to fail. It's a binary. Did it complete or did it not? Those are the only two choices. And lastly, which ACID property guarantees that one transaction cannot view the intermediate state of another transaction? Pause, think about it. And that is the isolated or isolation property. And that basically states, essentially what this states. If a transaction is running, you can't have another transaction peeking at the intermediate state of another transaction. That violates a whole bunch of other things. Okay, and let's just keep moving forward. And we'll skip through this. Okay. Next up, oh, pardon me, we'll just go ahead and check something. Sorry about that. For a second, I thought I was reading off the wrong slides, but I can confirm this is correct. All right, let's keep moving forward. First up, let's talk about database objects. So we talked about relational databases, and we talked about how there's a bunch of relations inside of relational databases, right? And those are kind of like your column row objects that keep track of data. But there's actually other things that exist within relational databases. We're going to skip this question because we actually didn't talk about these auxiliary objects too much. And instead, I'm just going to define them for you right off the bat. So there are three other objects that we could potentially have in a relational database. And this includes a view, an index, and finally, something called a stored procedure. Let's dive into what each of these terms actually mean. First up, a view. Well, you should actually be familiar with what a view is because you've used pandas before. And throughout your time using pandas, you should realize that oftentimes what you have created are views. And what is a view? Basically, think of it as just a specific subsection of the data frame, of the table. And this specific subset is something called a virtual table. Now, in Python pandas, we may have created a view using Boolean indexing or some other method. However, in SQL, we create views using the select query. So basically, everyone, what a view allows us to do is it encapsulates a select query into an alias that we can then treat as a real table. Now, one thing to note about views, and this is really, really important to note, is that virtual tables are never cached. Now, what does that mean? Basically, if you create a view, you're not creating a copy of the table. You're just basically creating a subsection of the table, or rather, you're just viewing a subsection of the table that you've aliased into one specific name. So what that means is that if you modify a view, guess what? You're modifying the original table as well. So that's something to really keep in mind, right? Because you don't want to create a view and pretend or assume that it's just a copy of a table and then modify it any way that you want, and then find out later, maybe a week from after your modification, that the modification that you did actually just influenced the original table, actually changed the information on the original table. So yeah, keep that in mind, everyone. Basically, a view is a virtual table that we create using the select query that is actually just a subsection or a subset of the original table. Here's what it looks like when we create a view in Microsoft SQL. As you can see, we type out create view and then the name, deliveries, as, and then afterwards, we just basically write a select query. Okay, let's keep moving forward. After view, we have something called an index. Now, the thing about SQL and the way information is stored on a SQL table is we usually have some sort of column, or we treat some column as the index in order to perform really, really fast access in our table, essentially. Now, by default, the primary key that we define is going to be our index. However, if you would like to treat a different column as an index, essentially what you can do is tell SQL, or basically write a query that basically states, hey, create an index on this specific column within this table. This essentially allows us to speed up our queries, and it's generally recommended that you do this if you're accessing a table according to one specific column constantly, right? Like, for example, if you have a table of product IDs, and let's say you are constantly looking for specific products based on their IDs, it would probably be advisable to create an index on that column so that you can speed up your queries. Now, the specific mechanisms as to what SQL does in order to speed up the queries is a topic that we're not going to get into in today's video. However, just for basic terminology purposes and just so that you know that this thing does exist, basically what SQL uses is something called a B tree. This is one of those fundamental data structures that you learn early on in your computer science journey, or maybe not early on, I would actually say a little bit after your computer science journey, once you start delving into fundamental data structures. And basically, this B tree is what we use in order to efficiently search for information based on a specific index. Take a look at these values and notice how we actually organize this. You should actually see how this supports really, really fast access time compared to just linearly looking through rows. Anyways, let's keep moving forward. All right, next up, we have stored procedures. Now, the answer on Google, when you look up what a stored procedure is essentially something that encapsulates programmatic logic in a database for actions that applications need to perform when working with data. This should be very reminiscent of what a function is in Python. Hopefully you all remember the concept of functions in Python. That's basically when you type in something like define, name, and then some sort of logic underneath it. It's essentially the same thing in SQL. You have something, or you have some sort of name that you are going to call every now and then whenever you want to execute some logical ordering of steps and actions. Now, here's something that's very, very important to note. A function in SQL is not the same as a stored procedure. I know it's a little confusing, right? So this stored procedure, something that kind of sounds like a function, is actually not, or rather we can't call it a function in SQL. Always keep that in mind. Maybe we'll talk a little bit more as to the differences between a function and a stored procedure later on. But for now, the most important thing for you to note is that stored procedures are what you use when you want to execute some series of logical steps on a table or within your database, essentially. All right, so those are our three auxiliary database objects. We have a view, an index, and finally a stored procedure. And if I were to just give you the Spark Notes version of these slides, I would say a view is something that optimizes data organization. An index is something that improves the speed of access. And finally, a stored procedure is something that, once again, encapsulates programmatic action, something that puts programmatic actions, a bunch of programmatic actions, all under one name, which makes it super convenient for you to call. Okay, here is a question, a review question that will hopefully test your knowledge on these objects that we just talked about. You are working with a business analyst. I don't know why I really emphasized you just now, but I did. Anyways, you're working with a business analyst who needs to run periodic reports to understand customer behavior. So essentially, your company has a relational database, and there's a bunch of customer events in this relational database, and your business analyst comes up to you and they say, hey, person XYZ name, I am always running this one specific select query in order to retrieve this specific data. How can, or which object can I use in order to retrieve this data? Pause for a second, think about this, and hopefully the answer that you're coming back with is a view, right? This business analyst constantly needs to view some specific subset of data, and they are always writing the same query over and over and over again. Well, guess what? They need a view. All right, let me know if you all have any questions on that question. Okay, next up, everyone, we have SQL. Let's see here. We'll talk about these discussion questions maybe during class. But yeah, let's get into the history of SQL. History is always fun, especially when you're talking about technology or the history of technology. It's always a good idea to look into the history of specific technologies that you're using, because it kind of reaffirms to yourself, okay, well, I'm using this tool because of reason X, Y, Z. And maybe you might even realize why you might not need to use a specific technology once you look into its history. Yeah, really, really fascinating stuff. Anyways, so Edgar F. Codd, aka the Codd father, back in his paper in the 1970 on relational databases, he wrote, changes in data representations will often be needed as a result of changes in query, update, and report traffic. I'm not exactly sure what he meant by traffic. I don't think he meant like, car traffic or pedestrian traffic. I think this was like some terminology related to the business needs of that day. But basically, he said, hey, programmers need to be able to query a database. They need to be able to write in some sort of language that alters the database. They can't be designing their own APIs for every single database that's invented. Can you imagine that? Can you imagine if during the fellowship, this paper never came out and we told you guys, hey, we have all this data, but guess what? No one's invented a way to interact with databases. So take your Python knowledge and invent us an API to work with this data. That would take a good while. In fact, the entire fellowship would probably be about API design. So once again, this is a very, very good idea because after Edgar F. Codd came out with this paper, the IBM computer scientists Chamberlain and Boyce basically developed a language called SQL, like literally SQL, SEQUEL. But later they had to change their name due to copyright infringement. There was actually something else called SQL. And it actually turns out, I forget the exact story, but someone was late to the patent office, so they didn't submit their name in time. So that was part of the reason why they had to name it SQL. Good fun. All right, so let's talk about the language of SQL, everyone. SQL is a good idea, hands down. And there's a lot of different dialects of SQL. The American National Standards Institute actually standardizes what SQL should look like. But on top of that, there's a bunch of other flavors of SQL that we can have. There's Transact SQL, PostgreSQL or PostgreSQL, procedural language SQL, which is Oracle. Excuse me. The SQL that we're going to talk about is T-SQL or Transact SQL. Pardon me. And that's essentially the Microsoft, or essentially what Microsoft SQL uses. All right. And I kind of skipped over this, but Microsoft SQL is what Azure uses as well. Hopefully, you know by now that Microsoft and Azure, or Azure is a product of Microsoft. So yeah, Microsoft SQL is definitely what Azure is going to be using as well. Now, the language of SQL, everyone, has three logical groups. There's actually more than three, but we're not going to get into them. We're only going to focus on these three. And truth be told, we can only focus on two and still be fine. But essentially, the three main logical groups include data definition language, data control language, and finally, data modification language. Dance Dance Revolution is not on this list, unfortunately. We only have DDL, DCL, and DML. Now, let's get into what these logical groups actually entail. Hopefully, just by looking at these names, you kind of get a sense of what the purpose of these languages are, or what these logical groups are, right? Data definition, data control, and data modification. Sounds pretty simple. All right, and yeah, here's just like a quick list of the different queries under DDL, DCL, and DML. First up, we have DDL, data definition language. This right here is the language of creation. This is the language that we use, or the logical group that we use, when we want to create, modify, and remove tables and database objects. So once again, now that we talk about databases, everyone, I don't want you to just think about tables. I also want you to think about views, procedures, and indices or indexes. Some common DDL statements include the create statement, the alter statement, the drop statement, and finally, the rename statement. And here's a little Civ 6 GIF. Civ 6, great video game. Highly encourage you to play it. Anyways, can't wait for Civ 7. Now, three of the four DDL statements that we talked about are usually one-liners. For example, alter table, the name of the table, and then some sort of action. Drop the table, name, rename the table, name, and so another name. We don't really have to get into too much detail with this, truth be told, because DP-900 won't be asking us questions related to this. But just for fun, let's go a little bit deeper into the create statement. So the create table query is one that we've learned within this fellowship. And basically, this is the query that we use when we are creating a relation. For example, we have create table product, ID in primary key, name, varchar not null, price decimal null. I'm actually missing commas between each one of these statements. Sorry about that. Just pretend that there are commas here. And let's break this statement down and see what each part actually means. So first part, create table product. That's simple enough. You're just creating a table named product. Now, in the first row, we have ID int primary key. Let's break that down. The name of this column is ID. The type is int. And the specialized keyword that we're using is primary key. And primary key basically states, hey, this column uniquely identifies the rest of the row. Think of this as like an ID number, a social security, some sort of important badge that we use in order to identify ourselves. This should be unique. There should not be any duplicates of IDs at all. And yeah, it should also uniquely identify some sort of entity or event. Okay, let's move on. Next, we have name varchar 20. So name is the name of the column. Varchar 20 basically means that this is a string with maximum 20 characters. And finally, not null basically means this cannot be null. When we're doing data entry, you cannot leave this empty. We cannot have a nameless person in our database or a nameless product in our database. AKA, this is a mandatory column. And finally, everyone, we have price decimal null. And this basically states, by default, this column is going to be null. And not only can it be null, but by default, it's going to be null as well. Anyways, let's keep moving forward. All right, everyone, next up, we have DCL, and this is data control language. This is essentially what we use in order to grant, deny, and revoke permissions of our database objects to different people. Whenever you start working with a larger organization, you really learn the lesson of not giving everyone access to everything, because that's just a recipe for disaster. I'll tell you all a little bit of a tangent or a little story of mine. So one time I was backing up some data to a 20 terabyte drive that was pretty much almost full. And when I plugged and this was for a job. And when I plugged my computer in, it asked me if I wanted to reformat this drive, basically delete all the data and start fresh. I thought I clicked no, but somehow through a mouse slip, I clicked yes. And I very quickly reformatted 20 terabytes of data. Basically, I lost almost 20 terabytes of data. Now, essentially, I'm telling you that story to tell you that a regular person or a basic employee should not be able to reformat a hard drive. There should be proper permissions in place so that accidents like that don't happen. And I'm not just saying that to shift the blame to someone else. Obviously, I messed up, but there should be stop guards in place, right? One catastrophic mistake should be able to be halted through proper permissions, and the DCL language will help you do something along those lines. Grant permissions to users, deny permissions to users, or revoke permissions that previously were there. And here's essentially what it looks like. All right. And then next up, everyone, we have DML, or the data modification language. And this is essentially used to query, insert, modify, or delete existing rows. Select from a table, insert into a table, update a table, or delete from a table. Yeah, the SQL or the basic select query is a pretty simple concept. This is the basic select from where that we learned about throughout this fellowship. Essentially, this tells us select from the table customer, and then filter where the city is Seattle. Simple as that. You can also include order by if you'd like, and you could also include group by. All concepts that we've gone through before. Let me know if you have any questions about this. Also, we have joins, which basically allows us to combine one table with another. And hopefully you also remember the different types of joins, right? There's left joins, right joins, inner joins, outer joins. This one right here is an example of an inner join. Okay, so just to wrap this up, we have DDL, used to create, modify, and remove tables. DCL, used to manage access to tables and objects. And finally, DML, used to manipulate, delete, and query rows. Okay, if you would like to practice your SQL, I recommend this lead code question right here. Pretty simple lead code question, nothing too serious. But essentially, that's going to be it for SQL. We might go over a couple of more review questions to prepare you for the Azure course or the DP-900 exam. But once again, they're not going to ask you complex queries. It's all going to be multiple choice. It's all going to be fill in the blank. So at most, they're going to ask you to fill in the blank of a SQL query. So yeah, we'll do a little bit of practice with that. All right, how am I on time? Let me check. All right, and let's finish up today, everyone, with a little bit of normalization. Once again, highly recommend for you to pause the video every now and then, get up, walk around, look outside. Really helps with knowledge retainment. Definitely don't recommend watching this all in one go. Unless you're doing something else, then I don't know, maybe that will work. Anyways, let's get into normalization. Now, the concept of normalization is honestly my favorite when it comes to relational databases, because once again, it's such a good idea. Shout out Edgar F. Codd. All right. Anyways, normalization is great. I know we spent a little bit of time in the fellowship talking about normalization, but I really feel like we could have given it more attention, and we'll definitely be doing that going forward. But I just want to reintroduce the concept of normalization to you all. So right off the bat, normalization is a mathematical concept. It's rooted in mathematics. And that's not surprising. Edgar F. Codd, after all, was a mathematician. He was not a programmer. He was not a computer scientist, if that concept even existed back then. He was a mathematician. And the concept of normalization is rooted in something called functional dependency. We're not going to get into this because honestly, it might be too much for the DP-900 exam, but I recommend that you do watch something about functional dependency. It's really interesting stuff. And at its heart, it's really like a game of mix and match. Anyways, here are the practical rules of normalization. Specifically third normal form. Each entity is in its own table. Each attribute is in its own column. Each row is uniquely identified using a primary key. And finally, foreign keys link related entities. Those are the four principles of normalization. It sounds obvious, and it sounds like that should be a given, but it's not, as we'll see in the next slide. Here's an example of a table without normalization. Take a look at this. Look at its columns, look at its rows. I want you to think, which rule is this table violating? Pause the video. Think about this for a little bit. Okay. Maybe you could have actually picked out a few. And in fact, actually, we're going to talk about every single rule that this table is violating. There are three entities in one row. Look, there's the customer, there's the product, and there's also an order. That's three entities right there. Columns include multiple or a lot of attributes in one column, or multiple attributes. And finally, primary keys are not unique. Check this out. We have order number 1000, order number 1000. That's not unique, right? That's kind of duplicated and a little bit confusing. Sure, maybe this person purchase multiple products, but there has to be a better way to present that. And furthermore, good luck finding Joe Jones, which is sometimes with a comma and sometimes with a dash. That's ridiculous. Also, good luck updating the price of a hammer, which is embedded into the name all around. This is a bad way to represent information, right? And normalization tells us that there is a better way to go about this via these 4 rules. And if we apply these 4 rules, we'll instead get something that looks like this. Notice how entities are in their own table. Notice that price and name are separated out. This right here, this is great. And furthermore, notice that even though entities are split into their own tables, it doesn't mean that they're not related to one another. We have something called a foreign key or an external key that relates this information. This is a beautiful way to represent information, and hence why it really lived or remained as a constant in database management for about 50 years at this point. Anyways. Now, normalization is great. Normalization has its use cases. It reduces data redundancy. It's perfect for relational OLTP databases. It reduces storage requirements. You're not duplicating information. The information isn't redundant. And it also improves something called data integrity. If you have less rows to update, there's a smaller probability that, or maybe no probability at all of you, pardon me, updating one row, but forgetting about another, right? Like going back to this table, let's say inflationary forces hit and we want to update the price of a hammer to $4. Okay, we updated here, but we clearly forgot about the hammer here. Yeah, and that's just going to make our lives even harder. So normalization is great for those reasons. However, just like everything else in technology, there are times when you want to apply something and times when you don't want to apply something. And sometimes normalization isn't the best. For example, if you want an analytical database, and if you'd like to do some analysis on sales, normalization is actually going to hinder these efforts, right? Everything is split out into different tables. So you're basically gonna have to figure out which joins you need in order to get your, analysis, which basically points to the fact that normalization does not satisfy analytical structures. So hopefully this really shows you the reason why we have 2 different solutions, OLTP and OLAP. OLTP is normalized. Everything is split into separate tables, et cetera, whereas OLAP, well, at that point, we're going to join everything back together, keep it static. We're not going to update it. And then we're going to allow our analysts to do analysis on our OLAP solutions. Yeah, so that's essentially the pros and cons of normalization. Now, let's do a little bit of a review. Take a look at this table. Is this table normalized? Pause for a second and think about it. Okay, hopefully your answer is an overwhelmingly resounding no. Let's write this out in all other languages. Нет. Nem. If I knew more languages, I would also, expand this list of no's. No, this table is not normalized. You have Killian Murphy, that's how you pronounce his name, and Florence Pugh, sorry, in the same column. Not a good idea. You have the Oppenheimer entity or the movie entity, the actor entity, and basically movie and actor all in the same table. Maybe this is great for analysis, not great for an OLTP database. All right, maybe in class we'll talk about how we can actually normalize this thing. But that's essentially going to be it for database normalization and SQL and database objects. Here's a little normalization joke. What should be normalized? The relational database. Next week, everyone, we're going to talk about we're going to pivot. We're going to get away from databases. We're going to get away from OLTP and OLAP and everything. And we're going to go back into the world of file storage, which is a little bit of a, not a more simple world, but a different overview on things. We're going to be talking about blobs, lakes, storage, and blob fishes. And yeah, that's basically going to be what's up next for next week. Thank you all for watching, and I hope to see you all next week.